Welcome back to Boring Astronomy. Last time, we returned from the vast, unsettling silence of deep space and took a guided tour of our immediate cosmic neighborhood, the solar system. We explored the quiet diversity of our planets, from the scorching plains of Mercury to the icy depths of the Kuiper Belt, each following its precise, predictable orbit around our constant sun. We saw how the mundane laws of physics govern this entire family, maintaining a cosmic clockwork that has ticked for billions of years. Tonight, we're going to look up, as humanity has done for millennia, at the familiar tapestry of the night sky and delve into the true nature of stars and constellations. They seem like static points of light, ancient patterns fixed in the heavens, but their boring consistency and immense distances hold a deeper, more profound meaning than their shimmering appearance might suggest. So, dim the lights, perhaps turn on a fan for that soft hum, and let's ease into tonight's journey together. You see them every clear night, countless pinpricks of light scattered across the darkness. We call them stars. They seem small, distant, almost insignificant, but the most fundamental and perhaps most boring truth about every single star you see is this: they are all distant suns. Each one is a colossal, incandescent ball of plasma, a massive nuclear fusion reactor, just like our own sun, but so incredibly far away that its immense light is reduced to a faint glimmer. They are not merely decorative elements in the night sky. They are the powerhouses of galaxies, the creators of the heavy elements that make up planets, and ultimately, us. Their light, often thousands or millions of years old, by the time it reaches your eyes, is a quiet, continuous message from the cosmic past, delivered with unwavering consistency. Why do they twinkle? It's one of the first questions we ask as children, and the answer, perhaps disappointingly, is entirely mundane. Stars themselves don't twinkle. Their light, having traveled unimaginable distances through the vacuum of space, reaches Earth as a steady, unwavering beam. The twinkling effect, or scintillation, is caused entirely by our own planet's atmosphere, that invisible shield we discussed a few episodes ago. As starlight passes through different layers of air, which have varying temperatures and densities, it gets slightly bent or refracted. These atmospheric layers are constantly shifting and swirling due to convection currents, like heat rising from pavement. So, as the light beam zigzags through these turbulent pockets, its apparent position and brightness fluctuates ever so slightly, creating that familiar, romantic twinkle. It's a boring, terrestrial phenomenon, a simple atmospheric distortion, not a property of the star itself. The closer a star is to the horizon, the more atmosphere its light has to pass through, and therefore, the more it will appear to twinkle. Now, let's talk about constellations. Since ancient times, people have looked up at the night sky and seen patterns. They connected these stars with imaginary lines, creating figures of heroes, animals, and mythical beasts. Orion the hunter, Ursa Major, the great bear, Leo the lion. These constellations are among the most enduring and boringly consistent human constructs in astronomy. The stars within a constellation are almost never physically related. They are simply stars that, from our unique vantage point on Earth, appear to be close together in the sky. If you were to travel to a different star system, even a relatively nearby one, these familiar patterns would completely break apart, replaced by new, unfamiliar arrangements of stars. Constellations are essentially cosmic optical illusions, a product of our perspective and our innate human desire to find order and meaning in randomness. The reason these constellations appear fixed, unchanging generation after generation is due to the truly vast distances to these stars. While stars are indeed moving, hurtling through the galaxy at incredible speeds, their immense separation from us means their apparent movement, known as proper motion, is incredibly slow from our perspective. It takes tens of thousands, even hundreds of thousands of years, for a star to visibly shift its position relative to its neighbors in a constellation. So, for all practical human purposes, The patterns of the Big Dipper, or Orion, are effectively permanent. This profound, boring constancy allowed ancient navigators to use the stars as unchanging guides, like a permanent cosmic map. It's the ultimate slow-motion ballet, a celestial performance that unfolds over timescales incomprehensible to human life. Stars also come in different colors, and this isn't a stylistic choice by the universe. It's a boring, direct indicator of their surface temperature. Just like a metal poker heats up and changes color from dull red to orange, then yellow, and eventually white-hot, or even blue-white. Stars exhibit the same principle. The coolest stars, with surface temperatures around 3000 Kelvin, appear red. Slightly hotter stars, like our Sun, appear yellow-white, with surface temperatures around 5800 Kelvin. The hottest stars, with surface temperatures exceeding 10,000 Kelvin, emit most of their light in the blue, and ultraviolet parts of the spectrum, appearing distinctly blue or blue-white to our eyes. So, when you see a reddish star like Betelgeuse in Orion, you're looking at a relatively cool giant, while a brilliant blue star like Rigel is a true cosmic inferno. It's a simple, predictable relationship between temperature and color, a boring physical law expressed on a grand scale. Stars, like all things, have life cycles, though these cycles unfold over unfathomable durations. They're born in vast, cold clouds of gas and dust called nebulae, slowly collapsing under their own gravity over millions of years until the core becomes hot and dense, enough to ignite nuclear fusion. This is their main sequence phase, the longest and most stable part of their lives, where they quietly fuse hydrogen into helium, just like our Sun is doing right now. For billions of years, a star like our Sun will continue this boring, consistent process, providing unwavering light and heat. Most stars spend the vast majority of their existence in this state of quiet equilibrium, a testament to the efficient, long-lasting nature of nuclear fusion. When a star finally begins to exhaust its hydrogen fuel, its life enters its predictable later stages. For a star like our Sun, it will swell into a red giant, shed its outer layers to form a beautiful, albeit brief, planetary nebula, and then quietly shrink into a white dwarf. A white dwarf is essentially a stellar remnant, a very dense, slowly cooling ember, still shining from residual heat, but no longer undergoing fusion. It will continue to cool over billions, even trillions of years, eventually becoming a cold, dark, black dwarf. This is the ultimate boring stellar demise, not a spectacular explosion, but a long, drawn-out cooling into cosmic obscurity. Only the most massive stars end their lives in spectacular supernova explosions, which are rare, fleeting events in the grand cosmic timeline, leading to neutron stars or black holes. But even these explosive deaths are the predictable outcome of specific stellar masses, consistent end to a specific type of star. The space between stars, even within a galaxy, is mind-bogglingly vast. While our galaxy is home to hundreds of billions of stars, the average distance between them is measured in light years. If our Sun were a grapefruit in New York City, the nearest star, Proxima Centauri, would be another grapefruit in Los Angeles. This immense emptiness ensures that stars rarely, if ever, collide directly. They simply orbit each other, or the galactic center, in a silent, ordered cosmic dance, never touching, always maintaining their vast, lonely distances. This immense, quiet separation means that, despite the billions of stars, the universe is mostly nothing. So, the next time you look up at the night sky and see those familiar constellations, remember their true nature. They are not merely pretty, static patterns. They are the distant, individual suns, each a colossal nuclear furnace, silently burning billions of miles away, their light taking years to reach us. They are a testament to the mundane physics that dictates their twinkling, the human tendency to find patterns in randomness, and the incomprehensible distances that make them appear fixed. They are the ancient lights, consistently performing their boring, yet profound role as the silent beacons of our universe, marking cosmic time and guiding our understanding of our place in the vastness. Next time on Boring Astronomy, we'll take a closer look at a particularly unremarkable yet fascinating part of our own solar system, the asteroid belt. We'll explore its rocky remnants, how they formed, and why this seemingly chaotic region is actually a quiet, predictable collection of cosmic debris.